So the chemical formula gives us a lot of information about the composition of the compound. And then if we combine it with the molar masses of the elements, we can get relative masses, relative quantities of each element. So one way to express this is the mass percent composition, or sometimes just called the mass percent. And this is the percent by mass of one of the elements in the compound. This is a useful thing to remember about percent. Percent is the part over the whole times 100. So if you remember that, a lot of times you can figure out percent recovery or whatever you need. Just try to remember, it's the part I'm interested in divided by the whole thing multiplied by 100. So for mass percent composition, we can do this from the formula of a compound. So if we know what the formula is, we can look at the mass of X in the compound divided by the mass of the entire compound. And the easiest thing to do here is just to choose 1 mole of the compound. Because then to calculate the mass of 1 mole is just the molar mass. And then we'll do an example and we'll see that you get the mass of the element out of that calculation very easily. For experimental data, you might have actual masses. You've got a mass of the element, and you have the mass of the compound that it came from, and so then you just plug those into the equation, the mass of the element divided by the mass of the compound. The percentages of each element should add up to 100, but sometimes due to rounding and measurement errors, it doesn't quite work out, and so if the difference is in the last significant figure, then we're not going to worry about it. So let's do an example. Acetic acid is the active ingredient in vinegar. Calculate the mass percent composition of oxygen in acetic acid. What kind of an acid is this? It's an oxyacid. It has oxygen in it. If we cover up the H, C2H3O2, that's one of those polyatomic ions, acetate. You change the 8 to ic, and you get acetic acid. So even though this one looks very complicated, it's following the same pattern. So we're looking for the percent of oxygen. So the mass percent of oxygen will equal the grams of oxygen divided by the grams of the whole thing times 100. When the equation says times 100%, percent ends up being the unit here. It does not mean the percent button on your calculator. That calculator is for business people who don't understand what they're doing, right? If you multiply by 100 and press the percent button, you're multiplying by 1 and you're going to get the wrong answer. It's just a unit. Don't ever touch the percent button on your calculator. It's no good in chemistry. Okay, so we need the mass of oxygen and the mass of acetic acid, but the problem doesn't tell us how big our sample is because it doesn't matter. The percent composition is the same whether I have a teaspoon of this or a tanker truck full of it. So we get to pick the amount. So we're going to choose 1 mole because it makes the calculations easier. So we just choose 1 mole. So can I calculate the mass of 1 mole of acetic acid? Sure, we just learned how to do that. The molar mass, right? So this formula H, C2H3O2, there's a reason that the H's are separated. This is the hydrogen that makes it an acid. When you dissolve it in water, that's the hydrogen that becomes the hydrogen ion. These other hydrogens stay with the acetate ion. That doesn't matter at all when we're calculating the molar mass. But sometimes people wonder, why aren't those together? See, and here comes Amtrak. Doesn't it sound more polite than the freight trains? Toot, toot. Yeah. This is so funny. So we can lump those together if we want. We can say, well, there's 4 hydrogens. Yeah, there's 4 hydrogens. So 4 times the mass of hydrogen. And 2 times the mass of carbon. and 2 times the mass of oxygen. .052. Okay, so I can put that in the denominator. So I'm doing 1 mole. 1 mole of acetate is 60.052 grams. So not acetate, acetic acid. What's the mass of oxygen in that amount of acetic acid? 32. It's right here. There's the oxygen. 2 times 16, 32 grams of oxygen. So the calculation ends up being a little easier that way. So 32 grams of oxygen times 100, and see how the grams cancel out? So 32.00 divided by 60.052 times 100. Now I'm getting a bunch of ridiculous digits. 53.2871 blah blah blah. How many significant figures should this probably have? 4. Because I was using 4 in my molar masses here. And so this one especially, 2 times 16 is 32. That's 4. So 53.29% oxygen. It is important to understand the rules of significant figures. What's more important than getting the exact correct number of significant figures is to get a reasonable number of significant figures. Okay. Any questions about this one? .29%. Sometimes we're given a mass percent composition because somebody figured it out, and that can be a very useful conversion factor. So another thing we should understand about percent is it literally means per 100. So in this example, Freon 112, 69.58% chlorine by mass. That means 69.58 grams of chlorine per 100 grams of compound. Because if I took this and calculated the percent chlorine would equal the mass of chlorine divided by the mass of the compound times 100, and I would get 69.58%. Right? So when you see percent, you can rewrite that as that many grams per 100 grams. Percent per 100. So we can do problems like this. What mass in grams of iron 3 oxide contains 58.7 grams of iron? Iron 3 oxide is 69.94% iron by mass. Well, when you're not sure how to approach a problem, try dimensional analysis first. Pull the numbers out and see if you can just do some stuff with the units. So I've got 58.7 grams of iron. And in this problem, it's important to specify grams of what? Because we've got grams of the compound and we've got grams of iron. And then I've got this percentage, 69.94. Instead of just saying percent, I'm going to translate that into grams per 100 grams. That's the percent by mass of iron, so that's grams of iron per gram of the iron. No, it's not hydroxide, it's oxide, iron oxide. Now you could do this without using the formula, Iron 3 is Fe3+, oxide is O2-. Choose your method of getting those together. It's Fe2O3. And what am I trying to find? What mass in grams of iron 3 oxide? So I've got these numbers over here, and then over on the right side, I want grams of the compound. I have to figure out how to get from one of those numbers to grams of iron oxide. I have this one with a single unit, and I have this one that's per. Probably the conversion factor. So starting with this one, grams of iron, going to grams of iron oxide. Oh, look, this relates those two directly. I drew this way over here, but it's really one step. So 58.7 grams of iron. And I'm going to grams of Fe2O3, and I want grams of iron down here, so the units cancel out. Here I've got, come on pointer. Here I've got a mass of iron, and iron is down here in the denominator, so the 69.94 goes down there. And it was per 100 grams of the Fe2O3. That would be an exact number because of the percentage business. So there we go. 58.7, punch it in right. 58.7 times 100 divided by 69.94. Equals 83.929 grams, 83.9 grams of Fe2O3. Is it reasonable? This is the mass of the compound that contains this much iron. So this number better be larger, right? Because you can't have a classroom of 75 and have 83 girls in it if there's only 75 people, right? It just doesn't work. This is not the only way to do this problem. Some of you are really good with percentages and you can just do all sorts of stuff. Go ahead and just use your percentage skills to do this. But if you're not great with percentages, I think this is the most straightforward way to do it. Any questions? $83.9. Well, we can also get conversion factors from chemical formulas, and this happens a lot more in chemistry than using percent compositions. If we look at this compound C2CL4F2, this gives us the relationship between atoms of carbon and atoms of fluorine, or atoms of carbon and molecules of the compound. And if it's the relationship between atoms and molecules, it's also between moles of atoms and moles of molecules. So directly from the chemical formula, we can say there are 2 moles of carbon for every mole of compound. And we're getting that from C2. There's 2 carbons in the formula. There's 2 moles of carbon in 1 mole of the compound. We could look at the chlorine. Well, there's 4 moles of chlorine in 1 mole of compound. What if we were interested in the fluorine? How many moles of fluorine? 2. Are we okay with that? It is just that easy. But these formulas give us relationships in moles, not in masses. Okay? Just the moles. So determine the mass of oxygen in a 7.2 gram sample of Al2SO43, aluminum sulfate. This problem would be a lot easier if we had the mass percent of oxygen, but they don't give it to us. We could calculate it, but it's actually not, that wouldn't be any faster than doing it the way I'm going to show you. So I've got one number here, 7.2 grams of the compound, Al2SO43. And what do I want to find? Mass of oxygen. So probably grams of oxygen. I don't have a mass percent composition, but I do have information from this formula. In 1 mole of this compound, how many moles of oxygen? 12. 12 moles of oxygen per 1 mole of Al2SO43. That's what we just looked at on the previous slide. So I have the relationship between the compound and the oxygen in moles. So this is another place I'm going to have moles in the middle. I can convert grams of the compound to moles of compound. Using the molar mass. And from the formula, I can convert moles of compound to moles of the element. And then using the molar mass of the element, I can go to grams of the element. Any questions about how I got the path? That's the hard part. Yeah.
Can you just go over that one more time?
Yeah. So I'm starting with 7.2 grams of aluminum sulfate because that's the only number in the problem. And then I know that I'm trying to find grams of oxygen because it says determine the mass of oxygen. And then I have to figure out how do I get from this mass of compound to mass of oxygen. I don't have a percent composition, but from the chemical formula, I know the relationship between moles of oxygen and moles of compound. Because the formula, Al2SO43, 3 times 4, there's 12 oxygens in 1 unit, so there's 12 moles of oxygen in 1 mole. So whenever we've got something missing in the middle, try moles. Moles in the middle. So I can go from grams of compound to moles of compound using the molar mass. I can use my relationship I got out of the formula to go from moles of compound to moles of one element. And then I can use the molar mass of oxygen to go from moles to grams of oxygen. Okay? And that really, really is the hardest part of this problem, is just figuring out how to solve it. The actual solving of it isn't so bad. So figure out the path, write it down, and then we can follow the path. Sometimes following the path is tedious, but it's just tedious. 7.2 grams, Al2SO43. So I've got 3 arrows. I'm going to have 3 fractions. On the next line, I've got moles of Al2SO43. Yes, it's tedious to write down all those letters. Just do it. And then I've got moles of oxygen. And then I've got grams of oxygen. Don't put any numbers in yet. And then down here, I've got grams of Al2SO43. Then moles of Al2SO43 and moles of oxygen. And these cancel. And these cancel. And those cancel. Patterns. This mole to mole one is actually the easiest because I don't have to calculate anything. This is from the formula. I want to know how many moles of oxygen are in 1 mole of the compound, and I already wrote it down up here. There's 12 moles of oxygen in 1 mole of compound. And then I need 2 molar masses, 1 for oxygen and 1 for that compound. The oxygen's easier, so I'm going to do that one first. What's the mass of 1 mole of oxygen? 16. We don't have to worry about it being diatomic or anything because it's not by itself. It's with these other elements, so it's not paired up. It's just oxygen, 16. And now we have to calculate. So 2 times the mass of aluminum. And how many sulfurs are in there? 3. 3 sulfurs and 12 oxygens. That sulfate is a little bit like a wagon, right? It's got 4 wheels in the body of the wagon, and we've got 3 of them. So then I have 3 wagon bodies and 12 wheels on my 3 wagons. .17 grams per mole. And again, I might have an extra digit. Should probably end right there, but it's okay. So 1 mole, 342.17 grams. Okay? Then I just multiply and divide as I go across. 7.2 divided by 342.17 times 12 times 16 so I made a mistake because I'm getting like 473,000 because I multiplied by 342 instead of dividing. So let's fix that. That looks better. Initial number had 2 sig figs, that's the smallest. So my answer is going to have 2 sig figs, 4.040 grams of oxygen, 4.0 grams. Is it reasonable? It needs to be smaller than the mass of the whole thing, right? The whole sample weighs 7.2 grams. What's the mass of oxygen in that? It's got to be smaller. So that's encouraging. Any questions? 4.0. You have the answers show up right up here in the corner.